Welcome to the world of digital electronics. To understand the computer system, you must first understand the basic building blocks which make it all possible. That is the purpose of this video. No matter how complicated a digital system may seem, it will be made up primarily of circuits referred to as gates. Gates are basically electronically controlled switches that are either on or off. To understand how these gates work, we will start with the basics. We will begin with the three simplest of the gate circuits: the AND gate, the OR gate, and the inverter. Here we see a simple circuit using two switches, A and B, and a lamp as the load. This simple circuit can be used to illustrate the basic operating principles of the AND gate. Switches A and B are normal open switches. You should also note that a truth table has been placed by the AND gate symbol. The truth table is used to indicate the electrical output transition which results from each combination of electrical states at the input. For binary circuits, these states may be classified as being either 0 or 1, high or low, true or false, on or off, or open and closed. For the examples used in this video, we shall use the terms high and low. A high will indicate a high energy state and the low will indicate a low energy state. Now let's examine this circuit and see how it works. As you may have already noticed, when neither switch is pressed, the lamp will not be on. At this point we could say switch A is low, switch B is low, and the output is low. This has been illustrated on our truth table, which shows a low on A, a low on B will produce a low at the output. Now let's energize switch A and see what happens. When the button on A is pressed, you will notice that the lamp did not turn on. Again, according to our truth table, we now have a high on A, a low on B, and a low at the output. Next, we will release the button on switch A and push in the button on switch B. Again, you will notice the lamp did not turn on. At this point, the truth table shows a low on A, a high on B, and a low at the output. Now suppose we push in switch A and switch B. When this happens, the lamp turns on. Our truth table now shows that a high on A and a high on B produces a high at the output. As you can see, the truth table is used to summarize the operation of the gate circuit. You also notice that for the AND gate circuit to produce a high, the output had to have a high at both inputs A and B. Now let's look at the OR gate. Here we see the OR gate being represented by a simple circuit consisting of a battery, two switches, and a lamp. But this circuit is different from the one previously shown in that switches A and B are now in parallel. Also shown in this illustration is the symbol for the OR gate as well as the truth table. We will now examine this circuit to see how it works. When neither switch is pressed, the lamp will not turn on. This is indicated on the truth table. The truth table shows a low on A and a low on B produces a low at the output. Now suppose we push the button down on switch A. As you notice, the lamp turned on. Our truth table now shows that a high on A and a low on B will produce a high at the output. Next, we will release switch A and push the button on switch B. Once again, the lamp is energized. The truth table now shows that a low on A and a high on B will result in a high at the output. As you may have noticed, we can produce a high at the output by pushing in the button on either switch A or switch B. Now suppose we push in switch A and switch B. Once again, the lamp will turn on and remain on. This is represented on the truth table as being a high on A, a high on B, which produces a high at the output. Next, we will examine the inverter gate. The switch used in the inverter circuit is different from those used to illustrate the AND gate and the OR gate. If you recall, the switches used for the AND gate and the OR gate were normal open switches. The switch used for this simple circuit is a normal closed switch. In this circuit, the lamp is normally energized. Only when the switch is open does the lamp turn off. Since the inverter has only one input and one output, it will have only two states of operation. As you can see from the truth table, when the input is high, the output will be low, and when the input is low, the output will be high. Basically, the inverter reverses or inverts the incoming signal. You will also hear this gate being referred to as a NOT gate. Now let's see what would happen if we combine two of these gates. Here we see the AND gate and the inverter or NOT gate. Also shown are the truth tables for the two gates. As you may recall, the AND gate had to have both an A and B high to produce a high output, while the inverter simply inverted the signal. Let's suppose we place a positive going signal into input A of the AND gate. Input B will remain low or at ground potential. We can see from the truth table for the AND gate that if there is a high on A and a low on B, then the output will be low. Since the low is being fed into the input of the inverter gate, we can see from the inverter gate's truth table that the low will be inverted to a high. Therefore, by making input A high and input B low on the AND gate, we can expect a high at the output of the inverter gate. Now let's make input A low and input B high. Once again, we can expect a high at the output of the inverter gate. Since A is low and B is high, the AND gate will produce a low into the inverter, which is then inverted into a high signal. Only by making both inputs A and B high can we force a low at the output of the inverter gate. Once again, by referring to the truth table, we see that when input A is high and input B is high, we get a high at the output of the AND gate. This high signal is fed into the inverter gate and is changed or inverted into a low. It is common to find both of these gates combined to form a circuit called a NAND gate. If you will notice, the symbol for a NAND gate looks very similar to the AND gate symbol, the only difference being the small circle placed at the output of the device. Since the NAND gate has an inverter gate built into its output, it will invert the signals coming from the AND gate portion of the device. Therefore, when both inputs are low, there will be a high output. When input A is high and input B is low, there will still be a high output. Also, when input A is low and input B is high, the output will remain high. Only by making both inputs A and B high can we make the output of the NAND gate low. Here we see the OR gate with an inverter gate. Also shown are both truth tables. If you will recall, when either input A or input B was high, it produced a high at the output of the OR gate. When the high from the OR gate is fed into the inverter circuit, it is changed into a low. The only possible combination for producing a high from this circuit is when there are lows at both inputs A and B. When inputs A and B are low, then the output of the inverter circuit will be a high. Once again, it is common to find both the OR gate and the inverter gate being used to form a common digital gate called the NOR gate. Notice the circle at the output of the gate symbol. Anytime you see this small circle being used on a gate, it indicates the signal is being inverted at that point. Most of the gates shown to this point have had only two inputs and one output. In today's modern circuit, it is common to find gates with 3 or even 4 inputs each. Even though these gates have more inputs, their basic operation is the same as their 2-input counterparts, which we have just discussed. Let's examine the 4-input AND gate first and look at these similarities. The 4-input AND gate is being illustrated with a simple series circuit consisting of 4 normal open switches and a lamp for the load. A truth table has also been shown beside the circuit, indicating the output state when all inputs are low. As you will notice, when switch A is energized, the lamp does not turn on. Therefore, we have a low at the output. This will be illustrated on the truth table as being a high on A and a low at switches B, C, and D, which produces a low at the output. Next, we release switch A and energize switch B. Again, the lamp did not turn on. This is shown on the truth table as a low on A, a high on B, and lows on C and D, which produces a low. After releasing switch B, we energize switch C and the lamp still remains turned off. By looking at the truth table, we can see a low on switches A, B, and D, and a high on switch C. The output still remains low. Next, by energizing only switch D, the lamp remains in an off mode. Once again, the truth tables show that a low on switches A, B, and C and a high on switch D will produce a low at the output. As you can readily see, by energizing only one switch at a time, the output of the circuit will remain in the low state. Therefore, to get the lamp to turn on, we must energize more than one switch at a time. However, in this circuit, even by energizing 2 or 3 of these switches at a time, the output remains low and the lamp does not turn on. Please examine some of the combinations on the truth table. Only when all of the switches are energized does the lamp turn on. This is indicated on the truth table as being a high on switches A, B, C, and D, which results in a high at the output. Now let's examine a 3-input OR gate. To do this, we will use a simple parallel switch circuit consisting of 3 switches with a lamp as the load at the output. Notice the switches are wired in a normal open configuration. By examining the truth table, you can see that the lamp will be lit for every combination except one. Only when none of the switches are energized will the lamp turn off. This is because if switch A or switch B or switch C or any combination of switches is energized, the current path will be completed and the lamp will turn on. As you have seen from these past 2 illustrations, the 2 input devices and the multi-input devices both operate on the same principle, in that the AND gates must have all the inputs high to produce a high output, and the OR gates have to have anywhere from 1 to all of the inputs high to produce a high output. We will now pause for a short review of the material just discussed. A truth table is used to illustrate the operating conditions of a given gate circuit. It will list all the various input and output combinations. The AND gate is only high at the output when all inputs are high. Essentially, we are saying when one input is high and all of the other inputs are high, it produces a high output. The OR gate, on the other hand, will produce a high at the output when any of the inputs are high. In other words, if one input or any of the inputs are high, it will produce a high at the output. The inverter gate, or NOT gate as it is sometimes called, is used to switch the signal from one state to the other. The NAND gate may be considered as being an AND gate followed by an inverter gate. The NAND gate symbol is distinguished by the small circle placed at the output end of the AND device. The NOR gate may be considered as being an OR gate followed by an inverter gate. The NOR gate symbol is recognized again by the small circle placed at the output end of the OR gate. Only 2 states of energy exist in a digital logic circuit. These 2 states may be referred to as being either high or low, on or off, true or false, or 0 or 1. The 0 represents a low state and the 1 a high state. Common gate circuits are also available with multiple inputs. These gates operate on the same principles as their 2-input counterparts. This concludes our first review. Here we see 2 more commonly used gates which are referred to as exclusive logic gates. Shown on the left is the exclusive OR gate, and shown on the right is the exclusive NOR gate. Notice the letters used to designate each gate. The first gate we shall observe is the exclusive OR gate. The exclusive OR gate is the most widely used in the exclusive logic family. This gate is used frequently in digital arithmetic circuits. Here we see an equivalent circuit of the exclusive OR gate. Notice that it consists of 2 inverters, 2 AND gates, and 1 OR gate. Let's examine the logic combinations of this gate. We will begin with both inputs in a low state of energy. When we apply a low on input A, it gives us a low on one half of gate A and a high on one half of gate B. This is because the low signal being applied to gate B had to go through an inverter before it reached the input of the gate. We also said that input B was low, so this gives us a low on the other half of gate B and a high on the bottom half of gate A. Remember, the inverter on gate A changed the low to a high before gate A received the signal. We now have a low signal and a high signal being applied at gate A. Since this is an AND gate, we know that a low signal and a high signal will produce a low output. Gate B also has a low signal and a high signal being applied at its inputs as well, therefore it will also have a low output. The low outputs from the two AND gates are then fed into an OR gate. As you will recall, two low inputs on the OR gate produced a low output. By referring to the truth table, you can see that a low on input A and a low on input B will produce a low at output C. Now let's see what happens if we make input B high while leaving input A low. The truth table shows that it should produce a high output from the device. We have already seen that a low on input A produces a low on one half of gate A and a high on one half of gate B. And when we apply a high on input B, it gives us a high on the second half of gate B and a low on the second half of gate A. This gives us two lows at the inputs of gate A and two highs at the inputs of gate B. Since gates A and B are both AND gates, we will have a low at the output of gate A and a high at the output of gate B. The OR gate, being fed by the two AND gates, now has a low from gate A and a high from gate B being fed into its inputs. Remember, if the OR gate has one input or the other, or both of its inputs high, then it will produce a high output. As you notice, this is in accordance with the truth table logic. Next, we will make input A high and input B low. Our truth table shows that there will be a high output at C. We will now see how this happens. When a high is applied at input A, it feeds a high into one half of gate A and a low into one half of gate B. When the low signal is applied at input B, it feeds a low into the second half of gate B and a high into the second half of gate A. Since gate A has two high inputs, it produces a high output, and since gate B has two low inputs, it produces a low output. This OR gate, being fed by the two AND gates, now sees a high and a low signal at its inputs. This causes the OR gate to produce a high output. As you can now see, a high at input A and a low at input B produced a high at output C. Now let's see what happens when we place a high at both inputs A and B. As you notice, the truth table shows there will be a low output. When input A is made high, it feeds a high signal into gate A and a low signal into gate B. And when input B is made high, it feeds the second half of gate B with a high signal and the second half of gate A with a low signal. Since gate A has a high input signal and a low input signal, it produces a low at the output. In the same respect, gate B will also produce a low output since it also has one high input and one low input. The two low inputs being fed into the OR gate will produce a low output, as you will notice on the truth table. You may have also noticed that the exclusive OR gate has a special characteristic of producing a low output with both input signals are the same. Next, we will examine the exclusive NOR gate. Here we see the equivalent circuit of the exclusive NOR gate. This circuit also uses two inverters, two AND gates, and one OR gate. As you can see from the truth table, when both inputs A and B are low, it produces a high at the output. To understand how this happens, we shall examine the equivalent circuit. When input A is low, the signal is fed into one half of gate B and into the inverter circuit before going into gate A. This changes the low into a high before going into gate A. When input B is made low, it is also fed into one half of gate B, and it also goes into an inverter circuit before going into gate A. Once again, the signal is changed into a high before going into gate A. Since gate A has two high inputs, it produces a high output. Gate B, on the other hand, has two low inputs, so it will produce a low output. When the OR gate sees a high input and a low input, it switches to a high state. As you see, we have proven that two low inputs will produce a high at the output, as was shown on the truth table. Next, we will examine the condition of the exclusive NOR gate when a low is applied at input A and a high is applied at input B. The truth table shows that the output will be low. As we have just seen, when input A is made low, it places a high at one input of gate A and a low at one input of gate B. But when input B is made high, it places a high at the other input of gate B and a low on the second input of gate A. The high and the low inputs being applied on gate A will force the gate to go to a low state since it is an AND gate. Gate B will also be low since it also has a low and a high input being applied. The OR gate now sees two low signals being applied at its inputs. Therefore, it will go to a low state. As you see, once again the truth table was correct. Now let's examine the condition of a high at input A and a low at input B. According to our truth table, the output will be a low. When input A is made high, it feeds a high into one half of gate B and a high into the inverter circuit at gate A. The inverter changes the signal into a low and feeds it into gate A. And when input B is made low, it places a low on the second input of gate B and a high on the second input of gate A. Remember, the signal first passes through an inverter circuit before reaching gate A. Since gates A and B are both AND gates, and they each have a high and low signal being applied at their inputs, they will produce a low at their outputs. The low signals from the AND gates are then fed into the inputs of the OR gate. This causes the OR gate to produce a low output, once again just as was indicated by the truth table. Next we shall see what happens when we make both inputs high. Our truth table shows that there will be a high output. As you can see, when input A is made high, it places a low at one input of gate A and a high at one input of gate B. When input B is made high, it feeds a high into the other input of gate B and a low into the other input of gate A. Gate A now has two low inputs, which causes it to produce a low at its output, and gate B now has two high inputs, which it causes it to produce a high output. This high output from gate B and low output from gate A is then fed into the OR gate. This causes the output of the OR gate to develop a high. There are many different types of logic families, each having its own particular characteristics. When designing these logic circuits, there is always a trade-off between switching speed and the power consumed. Notice, for example, that the emitter-coupled logic family is the fastest of the logic groups. It has a switching speed of only 1 to 2 nanoseconds, yet it will consume 40 milliwatts of power. Whereas the CMOS logic family has a switching speed of 25 nanoseconds and only consumes 10 nanowatts of power. This table was shown to you so you will become aware of and familiar with the different logic families that are used in various digital circuits. As you have noticed, each family has its own special combination of operating parameters which make them useful in specific types of applications. Before covering some of the more common logic families found in today's digital equipment, we will quickly review some of the material just discussed. The exclusive OR gate is another commonly found gate used in digital arithmetic circuits. The uniqueness of the exclusive OR gate is in its ability to produce a low output state when both inputs are at the same energy level. The letters XOR are often used to designate this gate circuit. To better understand the operation of the exclusive OR gate, you should use the equivalent circuit shown to you earlier in the program. If you will remember, this circuit consists of two AND gates, two inverter gates, and one OR gate. The exclusive NOR gate is another commonly found gate circuit used in digital arithmetic circuits. The exclusive NOR gate differs from the exclusive OR gate in that there is an inverter gate placed at its output. This causes the output to go high when both inputs are of the same state of energy. The letters XNOR are often used to designate the exclusive NOR gate circuit. To better understand the logic operation of the exclusive NOR gate, it is recommended that you study its equivalent circuit. As you can see, it also uses 2 inverter gates, 2 AND gates, and 1 OR gate. Notice also that the inverter gates are placed at both inputs of gate A. There are a wide variety of digital logic families which have been used or are currently being used in today's modern equipment. Each family has its own special characteristics and parameters. This concludes review number 2. We will now cover some of the more common logic families found in today's electronic equipment. The first family we shall cover is the TTL. TTL stands for transistor-transistor logic. The TTL logic is the most widely used of the logic families. There are 2 basic groups of TTL logic circuits. These are the 5400 group, which is used for military equipment, and the 7400 group, which is used for commercial equipment. The military group requires more rigid specifications than does the commercial group. Even though there are numerous TTL logic circuits available on today's market, they will all have 4 common characteristics. First, their supply voltage will be similar. Second, the noise immunity will be similar. Third, the fan-in will be limited to 1 per gate. And lastly, the fan-out will be limited to 10 per gate. The supply voltage for the TTL family will typically range from 3.5 to 5 volts. 5 volts is the maximum which should be applied to these logic devices. The TTL logic devices should never be subjected to a reverse or negative voltage. This could damage or even destroy the device. Noise is generally induced in TTL circuits from stray signals being induced by other components located near the device. These signals are generally induced by stray electromagnetic fields created when a gate or some similar device switches from cutoff to saturation. If an input of a TTL gate is left open or floating, it will act as though it had a 2 to 5 volt positive potential being applied. Therefore, unused inputs should always be tied to ground to prevent the possibility of noise being picked up or errors being induced into the logic. Fan-in is a term used to represent the number of gates which may feed into a single input of a logic device. The fan-in of a TTL device is only 1. In other words, a TTL will only accept 1 signal source per input. The fan-out, on the other hand, is used to represent the number of inputs to which the output of the device can supply energy. TTL gates must be capable of supplying 400 milliamps at its output and drive 10 standard TTL gates. The logic high level of the TTL logic family will typically be 5 volts, and the low logic level will typically range from 0.2 to 0.6 of a volt. The switching speed or propagation delay of a standard TTL device will be approximately 10 nanoseconds. The switching speed is the time required for the device to go from cutoff to saturation or from saturation to cutoff. The TTL device will generally consume about 10 milliwatts per gate. Another commonly found logic family is the CMOS family. CMOS ICs are constructed with complementary metal oxide semiconductor devices. The insulated gate in the CMOS device provides a very high input impedance. This causes the device to consume very small amounts of power. The power consumed by a typical CMOS gate will be about 0.01 microwatts. This makes the CMOS logic family ideally suited for battery-operated circuits. The CMOS equivalent of a TTL gate will have a prefix of 8800. This number indicates it is a CMOS device. CMOS operating voltage levels can range from 3 volts to 15 volts. Notice the difference in supply voltage requirements between the CMOS and TTL devices. A high output condition of the CMOS device will be almost equal to the supply voltage, and a low output condition will be around 1.2 volts. As was mentioned earlier, there is a trade-off between switching speed and power dissipation in all logic gates. The CMOS device is no exception. The switching speed of the CMOS gate is typically 25 nanoseconds. This makes this device much slower than its TTL counterpart. Presently, the TTL and CMOS logic families dominate the small-scale and medium-scale integrated digital circuits. Here we see another commonly used digital logic family. These logic devices are termed ECL, which stands for emitter-coupled logic. Internally, the emitter-coupled logic circuits will use NPN transistors with their emitters tied together. Notice in the schematic of an ECL gate, the emitters of Q1 and Q2 are tied together. Transistor Q1 is used for one input, and transistor Q2 is used for the other input. Also notice that this gate has two outputs. One comes from the emitter of transistor Q4, and the other comes from the emitter of transistor Q5. You may also have noticed that the symbol for the gate has an inverted output and a non-inverted output. This is the symbol of an ECL NOR-OR gate device. The emitter-coupled logic family is among the fastest of the digital family groups in use today. These devices are widely used in industry where cost is not the primary factor. The ECL devices are commonly found in high-speed computing systems. ECL circuits are designed so that the collector to emitter voltages are always above 0.3 of a volt. This keeps the transistors in an active mode of operation and avoids hard saturation when the transistors are turned on. The fastest ECL series available will have a propagation delay of only 1 nanosecond with a power dissipation of 60 milliwatts per gate. In another ECL series, the propagation delay is 2 nanoseconds with a power dissipation of only 25 milliwatts per gate. Notice the trade-off between speed and power dissipated. The faster the gate, the higher the power consumed. Next, we will examine the numbering systems used in digital circuits. However, let's pause for a short review of this most recently discussed material. TTL stands for transistor-transistor logic and is among the most widely used of the logic families. TTL devices are generally classed in the 7400 group for commercial use. Supply voltages for the TTL family will typically range from 3.5 to 5 volts, with 5 volts being the maximum allowable voltage. TTL devices should never be subjected to reverse voltages, since this could destroy the device. Inputs on TTL gates should never be left open or floating because stray signals from nearby circuits can be induced into the gate, which will cause errors in the logic information. Fan-in is a term used to represent the number of gates which may be fed into a single input of a logic device. Fan-out is a term used to represent the number of inputs that the output of a device can supply energy to. Another common logic family is the CMOS family. The CMOS devices will have a very high input impedance and will consume very small amounts of power. Emitter-coupled logic devices are among the fastest in the digital family groups. The fastest in the ECL series has a propagation delay or switching speed of only 1 nanosecond, but it will consume as much as 60 milliwatts of power per gate. This concludes review number 3. This portion of the video will cover the numbering system used in digital circuits. We will begin by examining the decimal system first. You have been taught from your childhood experiences with mathematics how to count from 1 to 10. Basically, you were learning the decimal numbering system. You learned that the decimal numbering system used 10 different symbols. These symbols were 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. The decimal numbering system also utilizes positional notation. This is the order of digits whereby the leftmost digit carries the largest value and the rightmost digit carries the smallest value. For example, the number 9,356 can be stated as having 9 1,000s, 3 100s, 5 10s, and 6 1s. The multipliers in this case, the 1,000, the 100, 10, and 1, are referred to as weights. Notice that these weights are all powers of 10. For example, 10 times 1 is 10. 10 to the second power, or 10 times 10, is 100, and 10 to the third power, or 10 times 10 times 10, is 1,000. So far, you have seen any numerical value can be expressed as a decimal number using positional notation, and the sum of the weighted symbols 0 through 9. Next, we will see that a numerical value may also be expressed as a binary number using positional notation. The weights of the binary numbers will be in powers of 2. Remember, the decimal numbers use weights which were in the powers of 10. The numerical symbols used for the binary numbering system are 0 and 1. Numbers in any given electronic system will be expressed as voltage levels, current levels, or magnetization levels. In principle, we could have 10 different energy level states to represent the 10 digits used in the decimal system. However, it would require a much more complex circuitry to distinguish between these various levels. To simplify this problem, the binary system is used since it has only 2 levels of energy. It is either on or off. This two-state system is much more efficient and much less costly to build. You will see that any numerical value may be represented by the binary system using positional notation. For example, a number with a binary weight of 32 will have a power of 2 to the 5th power. A single binary digit, the 0 or 1, is generally referred to as a bit. 4 bits are known as a nibble, and 2 nibbles make up a byte. Many computer systems will process a byte as a single unit. The byte shown here represents the decimal number 157. At this point, we will see how we acquired the decimal number 157 from the byte illustrated. We will convert from binary to decimal, then from decimal back to binary. As you recall, it was stated earlier that the most significant bit was on the left and the least significant bit would be on the right. These shall be abbreviated as MSB for most significant bit and LSB for least significant bit. Since we know that binary numbers are raised by the power of 2, they will double in value each time the positional notation moves one place to the left. As you can see, starting from right to left, the numbers double in magnitude for each position. Each bit is now assigned a certain value depending on its positional notation. When converting from binary to decimal, you simply add the values of each bit which contains a 1. As you can see in the byte being illustrated, we have 128 and a 16 and an 8 and a 4 and a 1. When we add 128 plus 16 plus 8 plus 4 plus 1, we acquire the sum of 157. Now let's change the value of the byte and see what the decimal number becomes. As you can see, we have 128, a 64, an 8, a 2, and a 1. When we add 128 plus 64 plus 8 plus 2 plus 1, we acquire a sum of 203 decimal. Suppose we had a binary number that was 10 bits long, like the one shown. What would the decimal equivalent of this number be? The answer is an easy one. First, we place our values above each of the bits, remembering that each value must double as it moves to the left. Then we simply add the values of each bit that has a 1. When we add 512 plus 64 plus 32 plus 8 plus 4 plus 2, we acquire the sum of 622 in decimal. Now suppose we need to convert a decimal number to binary. This will also be a very simple procedure. To convert a decimal number to binary, you first subtract the largest possible power of 2 and then keep subtracting the next largest possible power from the remainder placing ones in each column of the number you were able to subtract and zeros in the columns for the numbers you could not use. In our example, we see that 64 is the largest possible power of 2 that can be subtracted from 72, because the next largest power of 2 is 128. When we subtract 64 from 72, we have a remainder of 8. Since we used the 64, we place a 1 in the 64 column. Next, we see that 32 is larger than our remainder of 8, so we cannot use the 32. Therefore, a 0 is placed in the 32 column. Next, we see that 16 is also larger than our remainder of 8, so we cannot use this value either. So a 0 is placed in this column as well. Our next value is 8. Since our remainder is 8, we can subtract the remainder from this value. This leaves us with 0. We place a 1 in the 8 column since we used the value of 8. Since our remainder is now 0, we will not have a 4, a 2, or a 1. So all of these columns will have a 0 placed in them. It is important to note that even though the 4, the 2, and the 1 were not used, we still have to indicate with a bit that these values exist. Now let's convert a larger decimal number into binary. We will use the same process we have just described. Since the largest possible power of 2 we can subtract from the decimal number 1157 is 1024, we will place a 1 under this column. Then subtract the 1024 from 1157. This leaves a remainder of 133. We cannot subtract 512 from a remainder of 133, so we must place a 0 in the 512 column. We also cannot subtract 256 from our remainder of 133, so we will place a 0 in the 256 column. But we can subtract 128 from the remainder of 133, which leaves a new remainder of 5. Since we have used this value, we must put a 1 in the 128 column. We cannot subtract 64 from the remainder of 5, so a 0 goes into this column. Likewise, we cannot subtract 32 from the remainder of 5, so a 0 must go into this column. We can also see that the bit value of 16 cannot be subtracted from a remainder of 5, so a 0 will go into this column. The next bit value is 8, and it too cannot be subtracted from a remainder of 5, so a 0 goes into this column. Our next bit value can be subtracted from a remainder of 5. When we subtract the bit value of 4, we have a new remainder of 1. Since we used the bit value of 4, we will place a 1 in this column. Now we see we cannot subtract a bit value of 2 from a remainder of 1, so we place a 0 in the 2 column. Our final bit value is 1, and we have a remainder of 1, so we place a 1 in this column. As you now see, the binary equivalent of the decimal number 1157 is 1,001,000,101. With a little bit more practice, you will find that converting decimal numbers to binary and vice versa is a very uncomplicated operation. We will now pause for a short review of the material just discussed. The decimal number system utilizes 10 digits. These digits are 0 through 9. Each digit is assigned a value depending upon its positional notation. The leftmost digit will carry the largest value. The leftmost digit is often referred to as the most significant bit, or MSB, and the rightmost digit is referred to as the least significant bit, LSB. The binary number system uses only 2 digits. These digits are 0 and 1. The weight of binary numbers is computed in powers of 2. In other words, as the numbers move to the left, they double in magnitude. Binary numbers are used in logic circuits primarily because the system is less costly to build. A single binary digit is referred to as a bit. 4 bits are known as a nibble, and 2 nibbles form a byte. To convert a decimal number to binary, you first subtract the largest possible power of 2 and keep subtracting the largest possible power of 2 from the remainder. Ones are placed in the columns where a power of 2 can be subtracted, and zeros are placed in the others. To convert from binary number to a decimal, you simply add all the values together from the columns which contain a 1. This concludes review number 4. For arithmetic operations using the binary numbering system, there are several simple rules which must be followed. There are 4 rules for binary addition. These are 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 equals 0, carry 1. Let's look at an example for adding 1010 in binary with 1011 in binary. We have shown our example in both decimal and binary notation. We can see from the rules for addition that 0 plus 1 equals 1, so we place a 1 in the rightmost column. Next, the rules show that 1 plus 1 equals 0, carry 1, so we place a 0 in this column and carry 1. In the next column, we have 1 plus 0, and the rules show that 1 plus 0 equals 1, so we place a 1 in this column. In the last column, we have 1 plus 1, and we know that the rules say that equals 0, carry 1, so we place a 0 in that column. Since our problem has no additional columns, we will use the next most significant bit value, which in this case would be the 16. By converting our binary answer into decimal, we see that the binary number 10101 equals 21. There are also 4 simple rules for binary subtraction. They are 0 minus 0 equals 0, 0 minus 1 equals 1, borrow 1, 1 minus 0 equals 1, and 1 minus 1 equals 0. In our example, we have shown the decimal equivalent and the binary problem. Remember, we begin with the least significant bit and work toward the left and the MSB. When we subtract 1 from 0, the rule shows that the answer is 1 and borrow 1 from the next column. Therefore, we will place a 1 in this column and place a minus 1 in the next column. Since we now have a minus 1 and a plus 1 in the next column, this will equal 0. When we subtract a 0 from a 0, the rule shows the answer is 0, so we place a 0 in this column. In the next column, we again subtract a 1 from 0, which the rules show the result will be a 1, borrow 1. Therefore, we place a 1 in this column. In the next column, we have a minus 1 and a plus 1, so subtracting 1 from 1 gives us 0, making this column now 0 minus 0, which the rules show is 0, so this column gets a 0. In the last column, we have a 1 minus 1. According to the rules, the answer is 0, so we place a 0 in this column. When we convert the binary number 00101 into decimal, we find the answer is 5. Here we see the rules for binary multiplication. As you can see, 0 times 0 equals 0, 0 times 1 equals 0, 1 times 0 equals 0, and 1 times 1 equals 1. The process of binary multiplication is quite similar to decimal multiplication in that the multiplicand is multiplied by the least significant bit of the multiplier. However, the partial products are added at each step of the process. An example should clarify this procedure. In this example, we are multiplying 1101 by 100 binary. As you can see, the decimal equivalent is 4 times 13. First, we will multiply the least significant bit of the multiplier times the multiplicand. According to the rule, 0 times 1 is 0. 0 times 0 equals 0. 0 times 1 equals 0. And 0 times 1 equals 0. Now we will go to the next multiplier bit and perform the same process, but we will shift the first partial product 1 bit to the left. We see that 0 times 1 equals 0. 0 times 0 equals 0. 0 times 1 equals 0. And 0 times 1 equals 0. At this point, we add the partial products together using the binary addition rules. In binary addition, 0 plus 0 equals 0. So we will have zeros from the most significant bit to the least significant bit. Next, we multiply the most significant bit of the multiplier times the multiplicand, and we must also shift the next partial product 1 bit to the left from the previous shift. When we multiply 1 times 1, the product is 1. When we multiply 1 times 0, the product is 0. Again, we multiply 1 times 1, and the product is 1. And again, 1 times 1 equals 1. Next, we again add the two partial products using the rules of binary addition. Our answer is 110100 binary. When we convert this to decimal, we see that the answer is 52. Now we will examine binary division. The rules for binary division are the same as those used in the decimal system. For example, if we divide the binary number 1111110 by the binary number 110, the answer will be 10101. Let's work this problem to see how we acquired the answer. The smallest number that 110 will divide into is the first 3 bits of the dividend, which is 111. Therefore, we will place a 1 above the third bit and subtract the 110 from the 111. As you can see, this will leave a remainder of 1. At this point, we bring down the next bit, which is a 1. Since 110 will not divide into 11, we place a 0 above this bit. From here, we bring down the next bit, which is a 1, and place it to the right of our remainder. This gives us the number 111. So our divisor of 110 will divide into this number, so a 1 is placed above this bit, and we subtract 110 from 111. Once again, we have a remainder of 1. Now we bring down the next bit, which is a 1, and place it to the right of our remainder of 1. We see that the divisor of 110 will not divide into this number, so we place a 0 above the bit. From here we bring down the last bit, which is a 0, and place it beside the remainder of 11. This now makes our remainder 110. Since our divisor is 110, it will go into the remainder 1 time, leaving a remainder of 0. Since we are able to divide at this point, we place a 1 above the last bit. To verify that our calculation is correct, we simply convert our binary number into its decimal equivalent. We see that the decimal equivalent of the binary number 10101 is 21. This concludes our first video in the basics of digital. You have seen how the AND gate, OR gate, NAND gate, NOR gate, NOT gate, exclusive OR gate, and exclusive NOR gate function. You have also learned how to convert decimal numbers to binary and binary numbers to decimal, as well as how to add, subtract, multiply, and divide using the binary system. It is recommended that you view this video as many times as necessary until you become familiar with the information being presented to you. You will find that in your career as an electronic technician, You will need to know and understand the basics of digital to work on today's modern digital equipment.